Hello friends, welcome to this video. In this video we are going to work upon the biomedical image segmentation, and for that task we are going to use the famous UNET architecture. But this time we will replace its downsampling path, or we can say the encoder part of the UNET architecture, with a pre-trained model. This pre-trained model is going to be the MobileNet version 2, which is trained on the large ImageNet dataset. So we are going to integrate the pre-trained model, that is MobileNet version 2, in the UNET. Before moving on to the theoretical and implementation part of this video, make sure that you subscribe the channel and hit that bell icon for more such videos. Now let's go through a little bit theoretical part. What is MobileNet and what is UNET? So first of all, what is UNET? That is our base architecture. So UNET is a convolutional neural network that was developed for biomedical image segmentation at the computer science department of the University of Freiburg, Germany. This network is based on a fully convolutional network, and its architecture was modified and extended to work with fewer training images and to yield more precise segmentation. So in this figure you can see that this is the architecture of the UNET, and it shapes like English letter U. That's why it is also called UNET. So this architecture has three parts basically. First is contracting, or we can say the downsampling part, the left side of this architecture. Second is the bottleneck part, that is the part between the encoder, or we can say the downsampling path, and the upsampling path. And the third part is the expanding, or we can say the upsampling path, that is the right side of this architecture. So this encoder takes the image and learns the necessary feature and relevant information from the input, and this decoder, or the upsampling or expanding path, learns to generate the proper segmentation map, and at last it gives us a binary segmentation map. So the downsampling path, it consists of two 3x3 convolution, each followed by a rectified linear unit and a 2x2 max pooling operation with a stride 2 for downsampling. At each downsampling step we double the number of feature channel. So in this architecture you can see, first the number of feature channels are 64, then we double them to 128, and after that they are 256, then 512, and at the bottleneck part they became 1024. And this process goes to the reverse in the upsampling path, that is from 1024 it became 512, then 256, then at last it became to 128. Now is the upsampling path. Every step in the expansive path, or we can say the upsampling path, consists of an upsampling of the feature map followed by a 2x2 convolution, a concatenation with the corresponding feature map from the downsampling path, and two 3x3 convolution, each followed by a ReLU. So this right side is the upsampling path, where this binary segmentation map is formed, and it uses information from the encoder. Through the skip connections. These arrow, you can see these four arrows are the skip connections. So the skip connection from the downsampling path are connected with the feature map during upsampling path. These skip connections provide local information to global information while upsampling. Now after this is the final layer. At the final layer, a 1x1 convolution is used to map each feature vector to a desired number of classes. So that's about the UNET. Now next part is our pre-trained architecture or model, the MobileNet version 2. So MobileNet version 2 is an architecture that is optimized for mobile devices. It provides the state-of-the-art performance for mobile model on multiple tasks and benchmark, as well as across a spectrum of different model sizes. So in this figure you can see the architecture. How does the MobileNet is built? So what are the advantages of using MobileNet version 2 as a pre-trained encoder? First of all, the main advantage is that it has less parameter, due to which it is easy to train. And the next is, using a pre-trained encoder help the model to converge. Next, using a pre-trained encoder help the model to converge much faster in comparison with the non-pre-trained model, and it also helps the model to gain high performance as compared to a non-pre-trained model. Now these all are the theoretical part of this video. Now we'll move on to the coding part, the implementation part. and for this we are going to use the Python 3.8 and the TensorFlow. So these are all the libraries which we need during this implementation. Now we are using TensorFlow 2.2.0 version. Next we are going to seed the environment so that the results are reproducible. Next we are going to set some hyperparameter. The image size is 256. We are going to train it on 30 POCs. You can train it on more. If I train it on more, then it's going to take much time. So for this demo purpose, I'm going to train it on 30 POC or maybe less, depend upon the time. The learning rate is 1e minus 4, batch size 8. You can increase or decrease the batch size up to your requirement. Currently I'm setting it to 8. Next we will see how we can increase it. Now next part is the dataset. For this biomedical image segmentation task, what dataset we are using? And for this we are using the clinic DB dataset, that is a polyp segmentation dataset, or we can say the clinics the CVC 612 dataset. You can get more information about this dataset from this link, or you can directly download it from the Dropbox. It contains these images and their respective binary mask. So we are going to give input images to the architecture and get the output as a binary segmentation mask. So now we'll start writing the code for this. First of all, we are going to load the data and split it into 3, that is training, validation and testing, with a ratio of 80:10:10. So 80% data for training, 10% for validation and 10% for testing. Load data. Next is the path, split 0.1% for testing and validation purposes. I already have this dataset downloaded here, so it has images folder and a mask folder. Okay, now let's get back to the code. Images. First join the path. Images /star, and like this masks path dot join path the masks /star. Now we are going to use the globe to get the path of all the images and their respective mask. After that we are going to sort the list of path to make sure that there's a proper naming is there, so that it's all the name gets sorted, all the path gets sorted, so a respective image have the respective mask in the list. Okay, so now we have the list of images and path, images and mask. Total size of images is images or mask is image, len images, valid size is equals to int, split into total size. Like this, test size is int, split into total size. I'm here using 80:10:10. You can change it accordingly. Train x valid x is equals to train test split images, the test size is valid size, and at last providing the variable called random state, which makes sure that we get the same result every time. Now we're going to copy this on this line, and like this we're going to generate the train x, train y, and valid x, valid y. And here instead of image we will replace it with masks. Like this we're going to generate the test set valid this time test x and test y. Okay, instead of images, train x and train y. Instead of valid size, it should be test size. I know that test size and valid size are same, but please make sure that you use the proper variable. If you by chance you want to change them, then it will be better for you. Test x, it will give the train x and the train y first, then valid x, or it should be small, valid y, and at last it should give test x, test y. So this is the function. Now we are going to next write a function that is going to take the path of image and mask and give us a numpy array of numpy def read image path. First of all, we are going to decode the path as we are going to use this function in the TF data pipeline. Next, we are going to read the image as an RGB path CV2 IM read color. Next, x is equals to CV2 dot resize. We are going to resize them to a specific size, that is image size we specified above. Next, we are going to normalize the value of the pixels between 0 and 1 by dividing them with the maximum pixel value, that is 255, and then return the x. Like this, we are going to write the function for the read mask path. Same path equals to path dot decode x is equal to cv2 dot im read x not x, that is path, and this time we'll read it as a grayscale image. For that we will write cv2 dot im read grayscale, and spelling is grayscale. Make sure that you write gray, not grey. Next is the resizing. We can copy it, and then normalization. Okay, so one more thing we will do here. The size of the x till now here is 256 by 256, but we need to convert it to 256 by 256 by 1. So we will make sure that we apply another function called np.expand dimension, expand dims. So it will expand dimension at the last axis. So it will change its add a dimension, and it will be of proper shape. Now we have write these two functions, read image and read mask, for the TF data pipeline. So we start write the function to build the TF data pipeline. First of all, we write TF dataset x y. So x is the path that x is the list that contain all the path for the images, and y is a list that contain the path for the respective mask, and a batch size is also needed. Batch is 8, by default is 8. If you do not provide, 8 is applied. Dataset is equal to tf dot data dot dataset from tensor slices. Now x and y. Okay, now next is dataset is equals to tf dot map. Now here we need to write a function. We haven't written this function, we're going to write it. TF dot parse map, TF parse. Okay, it should not be TF, it should be dataset. Okay, my mistake. So dataset is equals to dataset dot map TF parse. So TF parse function we are going to write now. What it will do, it will the TensorFlow TF that TensorFlow give it a path for a single image and single mask, and it should return the numpy array. Okay, so we're going to write it now. After this code, dataset dot batch, then we set the batch size. After that, dataset is equals to dataset dot repeat, then we will return the dataset. Now we are going to write the function tf parse above this function. But it will take a single x and y, so it's going to be a single x and single y, only a single path, not an entire list. Okay, def parse, again a function that will take single x and single y. Single x is equals to read image sx and single y is read mask sy. Now it will return sx and sy. Okay, now we will see we have sx sy. Now we need to convert this numpy function to a format that it is usable by TensorFlow, and for that we will use tf.numpy underscore function. First we will write the name of the function, that is parse. Second, the input the function will take. Third, the data type, the output of the data type, that is sx and sy here. So these are floats, 64 values, which we can specify TensorFlow tf.float 64. Next we need to set shape for this. So sx shape is 256 by 256 by 3 because it's an RGB image, and sy though set shape it is 256 by 256 by 1 as it's a grayscale. Now we will return sx and sy. Okay, so these two functions are required for building the TF data pipeline. So this is also complete, done. Now what we'll do, we will load the dataset, this dataset, and try to visualize it and see what is the size of the training dataset, what is the size for validation dataset and the test. So load data path. Okay, now let's write something here. Training data is length of train x, like this. Validation data len valid x. Print testing data len test x. Okay, so we have 490 images for the training, 61 for validation and 61 for testing. Okay, now again now what we will do, we will visualize the images and see how these images look. Now before that I will write a function that will read the image and convert it to proper format, read and RGB. So it will take an x, that is the path, and x is cv read the path x, and now we will try to convert it to proper format. The image here is a BGR format. You will see why I am saying a BGR format. So I am writing the function before only. cv2.cvt color x and cv2 color BGR to RGB. Okay. Now we will return x. Okay, this function also return. Now we will use matplotlib for the visualization. fig.subplot. They will display 4 images and then 4 masks respectively. So 1, 4, 1 and img plot, it should be now plt show. Now here we will use this read and RGB function, train x 0. Okay, now again we will use this function, but this time we will change the value from 1 to 2 and here 0 to 1, and we need to add one more thing here. image plot dot set CLIM 0.0, 0.7. like this. We will write it 2 more time for the images, 3 here, and you can write it in a loop also, but I am just writing it manually. 14, a difference of 0.7 should be there always. 4, so this is the fourth subplot containing this RGB image. Should be 3 and should 4, and here should be 2.1. now let's run this. Okay, there's some problem. Let's figure it out. What's the problem? So fig has no attribute subplot. Okay, I am write the incorrect. It should be add underscore subplot. Let's replace it. Now we will see. Okay, again some problem. Okay, again spelling mistake. Should be PLT. So much incorrectness. So these are the, you can see again we haven't got anything. So there is some problem and we will find out what this problem is. So these problems and errors are part of your daily life, so you need to work with them. So we'll see x0 image plot PLT show read and RGB train x0. Okay, so I have written the code correctly. Now we'll run it and see. So you can see 4 images, 4 RGB images we can see clearly. Now we'll see their respective mask like this. The same procedure, we'll copy this properly because we'll use the same code, but this time train X is replaced with train Y. Okay, so you can see that now you can see the mask also, the images and their respective mask. Okay, so this is all about the dataset. Now we will move on to the model part. We will write our main part here is the integrating MobileNet version 2 with the UNET model. First, the input shape is image size is 3, name is equals to input image. Now we will call our encoder, the pre-trained encoder, MobileNet version 2 input tensor we will specify as inputs. Next is the weight, the pre-trained weight, that is ImageNet, and include top equal to false, and we'll set the value of alpha also to 3.35. Can increase the value of alpha and the model complexity, the trainable parameter will also increase. Now what we'll do, encoder dot summary, we need to extract the proper skip connection from this. So we will first see the summary of the pre-trained architecture here. So it will give a warning, but ignore that, that's not a problem. So let me just write another variable, skip connection name. So first is that is first one, 256 by 256 by 3 input image. Next is for a 128 by 128, and that is the last here is this, the block 1 underscore expand underscore reload. It's always reload. always make sure that you take skip connection, which is an activation function, output of an activation function. Next is 64. So we'll move down and see 65, and before that we have this block 3 expand reload. And next is for 32. Let's move down. You can see block 6 expand reload. So that's these 4 are enough. Now the output, encoder output for the 16. Let's move it. Okay, we have got the block 13 expand reload. Okay, encoder dot get layer dot output. So we need the output of this layer. Now we have the name of the skip connections and the output of the pretrained encoder. Pretrained encoder. Now our main task is to write the decoder. We'll write the number of filter channels for this. I am writing reduce very less filter channels. You can change them according to you, because if I write like 64, 120, that it will take a lot of time for me to train the entire network, and that's not possible in this video. Encoder output. Okay, now we'll write a loop for I in range, because we have 4 skip connections and we write 4 blocks in this 4, so value of 4. So 1 len f, that is feature, number of feature channels plus 1. So we want to start the value of I with 1, because the output, first let me show you the output of this. So you already know the output of this encoder output is 16 by 16. So I will upsample it to 32 by 32, then we will concatenate it with this last. So we will move in the reverse order here and also here. So that's why I will start this value with 1, not with 0, so we can get this value properly. Like, let's extract the skip connection first. Encoder dot get layer. Okay, skip connection name minus I. Okay, dot output. So now I will print the shape of all the skip connection. Okay, let's see. Okay, you can see the shape. First is 32, then is 64, then 120, then 256. So we are getting the shape correctly. Now we will perform an upsampling, a 2 by 2 upsampling on the encoder output, that is this X, and after that we will concatenate this upsampled output with the skip connection from the encoder. Okay, now we will perform a 3 by 3 convolution followed by redo, but we also add a batch normalization in between. Con 2D, number of feature channel f minus 1, 3 by 3, the size of the filter or kernel padding should be same, the X, then batch normalization X, then activation reload activation in encoder, and the sigmoid activation in the output layer, the final layer that will generate the masks. Okay, now this encoder is complete. Now we will move to the output layer, and for that we will have a convolution layer with the feature channel 1, because this because number of classes is only 1, that is the white pixels, and the background are just nothing. Padding is equals to same x, and the activation is sigmoid. So now we have just completed the integration of the MobileNet version 2 with the UNET input x. Now we'll return the model. So this is complete. So model, okay, let me change the name, maybe it will create some confusion. Build model. So model is equals to build model, and model dot summary. Let's print the summary. Okay, I need to run it again. Build summary. So you can see the summary of the model has been printed on the screen. Now we'll see. So we have very less trainable parameter, that is 4,09,025 parameter. Now we'll define some matrix. We will write two matrix. Use two matrix mainly. That is the dice coefficient. Let's use dice coefficient recall, and also one is a precision. So we'll use three matrix. So I will define the dice coefficient here. Oh, this is the value for the smooth, that is 1e minus 50. I will tell you why I'm defining this here. Dice coefficient y true, y pred. Okay, now y true is equals to flatten. Now we'll flatten all the pixels in this y true, like we will do with the y pred, the prediction. Okay, now we'll calculate the value for the intersection. Section is equals to tf dot reduce sum it will calculate the sum for all the pixels y pred. Return 2 into intersection plus smooth divided by tf dot reduce sum y true plus tf dot reduce sum y pred plus smooth. So we have added smooth on the both side of the equation, that is this visible. We have added smooth in the numerator and also in the denominator. So if by chance the value of numerator or denominator is 0 and there is a chance of divisible by 0, it will cause an error. So we will add a small value so that there is no problem of divisible by 0. This is the function we define for dice coefficient. Now for the dice loss, again y true and y pred, that is y predicted value. Return 1.0 minus dice coefficient y true and y predicted value. Okay, so this is the metric we have defined. Now we'll start the training. First we will define the data set. Train x, train y, and the base size. Like this we will define the valid data set. Here valid x and the valid y. Next we will define some of the things like optimizer tf dot keras dot optimizer dot atom with learning rate LR. Matrix we will define as dice coefficient recall precision, and after that we'll compile the model. Dice loss optimizer is equals to Adam, that is operating variable, matrix is equals to matrix. Okay, now we compile the model. Okay, spelling mistake, it's optimizers. Again dice loss. Okay, now I think it should be correct, no error. Okay, now we'll define some callbacks. Reduce LR on plateau, monitor, validation loss, factor 0.1. So it will reduce the learning rate if there's a if the patience letter patience 4. So what this function is do, that is this callback reduce LR on plateau. If there is a constant, there is no improvement, or the loss validation load does not decrease continuously in 4 epochs, then it will reduce the learning rate by this factor 0.1. Next is the early stopping. Monitor, again validation loss, patience 10. So what this early stopping does is, if just imagine the validation loss does not decrease up to 10 epochs continuously, then the training will be stopped. So these are the callbacks. Now we'll define some step that will directly link to the training. So the training steps, the number of batch size, the number of batches in a one epoch we'll define here. Train x divided by batch. Like this, we'll define the valid step, len valid x batch. Now this only works if the number of size is even. If it is odd, then it will create some problem. So we'll make sure that we'll write that correctly. Is should be like this: train x models batch size. If it's not equal to 0, this means that some data is still remaining, so we should increase the test step by 1. And like this we will do with the validation step, valid x. Okay, now we'll call our last function, that is the main function, which is used to train the model, that is model.fit. Train dataset, next validation data is valid dataset. Next epoch, step per epoch. Step per epoch, we need to define the training step, train steps. Now validation steps, validation steps, valid steps. Next is the callbacks. So now it will start the training. Okay, we have some error. Then flatten, the spelling mistake, flatten, FLATTEN, flatten. Okay, it should be keras.layer. So many mistakes I do, but we learn only by our mistakes. I will run this function, and now we will run it here. See if there's any problem. Okay, I need to run everything again. So what I'll do is restart and run all. Run the entire notebook again. Okay, now it's building this summary. Okay, now with this step, now we'll see Again any problem, we will see. Okay, now we have again problem. SY reference before assignment. Okay, there's some problem with the TF pipeline, the TF data set, the data set functions here. Okay, we will make sure that no error is there. Let's again go back to the error and see the line number where the error started. Right, okay, it's not a Python file. So there is some problem with the local variable sy reference before assignment. We'll check every step to make sure that no error is there. sx, sx, sy, and it return sx and sy. Okay, it should be correct. Now sx, sy. Now I'm not getting where lies the problem. Where is the problem? Let's make sure to write it x and y. This make the thing little bit of clear. It will create some confusion. Here it's x and y. X is read made x, y is read mask y and return xy. Okay, now we have sx. From there sx numpy function parse sx float 64. We'll see if there's any problem. Again. Let's hope we shouldn't get any. Okay, so we have solved our problem. There's some confusion between sx and sy, so we have replaced the name of the variable and it's working now. So you can see the training has started. So till the training completes, we can write other functions, like we can write the function for evaluation and checking the result, the quality of mask. The test dataset is TF dataset, test x, test y, then the batch. Okay, it should be capital. Okay, now we will have to write the test step also, the number of batches, len test x divided by batch. If len test x divided by batch is not equal to 0, then we increase the test step by 1. Okay, now this is complete. Now we'll write the function for the image. For getting the result, we will see how the mask look. So for that we need to copy some function, these two functions from above, these two, we require them. We need to write them again, but with some little changes. We do not require that decode step here. And here we also do not require the decode step. Okay, now this is complete. I will write again a function. Okay, not here, here. Okay, def mask parse. This function we will require as we need to save the image, so we need to make sure that all the channels, all the images have same channels. Like an image, input image have 3 channels, that's RGB, but the ground truth mask and the predicted mask will have only 1 channel. So we'll make sure that the mask that is 1 channel have 3 channels. So we'll first squeeze the mask, then we will mask. Okay, then mask is equals to mask dot transport. So there's a lot of mask here, but don't worry, everything will be correct. If there's an error, I will solve it here only. Okay, now this is complete. Now is our function which will help us in writing, which will help us to see comparison of the ground truth and the predicted mass. That is the main thing we need to do. Let's see the training. Okay, it's can see. Okay, with the validation loss, you can see there's a, so what's the validation loss in? Starting at 81, then we can say decrease and validation of the dice, the validation dice. Okay, it's increasing. So training is going fine. So first we will create a loop xy and enumerate test zip, test x and test y. Okay, so we do not want to check the whole images, we just want some images, like 10 images. First we will read image x, y is read image, read mask y. Now we have the image and mask. We'll make a prediction, model.predict expanding the dimension x on the 0th axis, and then extracting the, because we have, so what we have done here still now, the we have, so the size of this is now is like this. I will tell you, it's like 1,256,256,3. okay, so output will also the shape of output like this. Ypred is here is like this. So 1 comma, so we'll extract is only, so we need to extract this value 256 by 256 by 1. So like a 0 here and applying a threshold 0.5. so this will turn, if any pixel value is greater than 0.5 it will turn 1 and rest will turn 0. So proper 0 and 1 should be there, so it will help us to see the mask more clearly. Now create a white line between that will separate those that image, ground truth mask and the predicted mask. Height 10 and 3. So let's all the images, align all the images x. Now we'll x, then y. X is RG image, y is the ground truth, and then the Ypred, that is a predicted value. So it will be not white line, it should be white line. White line, comma, and this y should pass through the mask parse function. Okay, and same with this also, mask parse and the white line. Now we will concatenate all the images, a single image, np dot concatenate all images axis as one. Now we'll again use that matplotlib function, plt dot figure, fig size is 12 by 12. okay, now a is equals to fig dot add subplot, one by one by one. Now show. So that's the function I've written. So training is complete, and we have the validation loss 0.37, validation dice coefficient 62, recall 71, precision 68, and learning rate 1e minus 4. Now let's check the evaluation. Okay, we have just written the test test dataset and test time. We haven't tried the model code for the evaluation. Evaluate the test dataset and steps equals to test steps. Okay, now let's now so the evaluation is done there. So the loss value on the test dataset is 0.30, test dice coefficient is 0.69, test recall is 0.81, and precision is 0.77. now let's move forward to these functions, and now we'll see. Okay, there's some now this is incorrect. So now we will see the predicted mass. Okay, now let me check the error again here. Okay, it should be mask. Okay, I get it. What's the problem? Okay, here should be not mask, it should be NP. Again this PLT problem. I always get this PLT problem. I never figure out what my problem is, what incorrect thing I have written here. Fig dot add subplot 1, 1, it should be like this. Again a big white image and the thing is there, so I have to check it again. Fig dot add subplot. Okay, so I've written the code successfully. Now we will run it and check for any problem. Okay, you can see the image, the first column of the images. Here is the real input, but you can see it's again in BGR format, not RGB. The second is the ground truth mask, that is the real value of the mask, the polyp, and the third column is the predicted mask, that is predicted by our model, that is mobile unit. So first we'll convert this BGR to RGB and we'll make changes here. X is equals to cv2 dot cvt capital C color x cv2 dot color dot underscore bgr to RGB. Okay, now you can see the image in the RGB format. That's why in the above I have written this code before only, that is here this read RGB, read and RGB function. So here also you will get BGR if I haven't tried this function. Now let's again move back on our mask. So you can see the masks. So you can see some masks are good and some are bad, some are just okay. So you can see the first one is not good, the second one is okay, third one you can say not good, fourth one absolutely bad, fifth okay, then it's good, the next is good. So you can see we have a decent training, so we have decent result. That's not too bad, not too good, we can say. These are just okay for this demo purpose. So what you can do to increase the improve the result? First of all, you can use the data augmentation. If there is more data, then you can have more features to learn, so the model will improve and give more result. You can also increase the epochs. Okay, so another thing you can do is you can change the pre-trained encoder. I've used MobileNet version 2. You can use ResNet 50 or DenseNet, but don't worry, in my future videos I will show you how to integrate those pre-trained encoders also in the UNET. Or you can use different decoder or different blocks in the decoder. Like here we are using 3x3 convolution. You can use a residual block or a DenseNet block. Like this you can improve the result. Now one thing you can do in every model is tuning your hyperparameter, like learning rate, epochs, the size of the model. So these are the things you can tune up. Now you can follow me on the social media, my social media like YouTube, Facebook, Twitter, Instagram, and if you like my work, then you can support me on Patreon. And if you find this work useful, make sure that you like this video and share it with your friends. So thank you, have a nice day.